Now I'm happy to introduce Manu Kapur from ETH Zurich. For the keynote, he's been in Singapore for a long time and then spent a brief period in Hong Kong and then joined ETH in Zurich. And obviously ETH was happy with the research that he and his group did, because they're expanding this line of research and hired new professors in this area. And interestingly, we always talk about cross-disciplinary research and bringing together different parts. I think this is a very nice example, because his professorship is also not directly tied to one faculty, but spans different faculties. So let's welcome Manu for his keynote.
Okay, I'll just say my thanks first. It's a pleasure. Thank you for the introduction, and thank you for inviting me. This is my first time in 35 years. I don't want to think about what I was doing 35 years ago as a teenager, but finally the invitation came. All right, so my name is Manu. I'm a professor at ETH Zurich, and today I'm going to talk about productive failure in learning technologies, literally in two parts. The first part, productive failure, and the second part, we'll talk about learning technologies, right? Okay, what do I do? A very sort of brief context in which I operate. I direct the Future Learning Initiative at ETH. It's a university-wide initiative recognizing that transforming learning and higher education practice cannot be housed in one place. It is through interdisciplinary collaborations with other professors. So we have about 20-odd professors from 12 different departments at ETH coming together to look at learning, both in a fundamental sense, in the basic research, but also in the applied, so to build technologies and applications and interventions. And when I talk about learning in the fundamental sense, we're looking at learning at the neural, even physiological basis of learning, neural basis of learning, cognition, affect, embodiment, social, cultural, depending on who I'm collaborating with and how we define the problem in that context. We are examining learning at these multiple layers of complexity. And then we build applications and interventions, because that's the second goal of my professorship, to actually change educational practice in higher education, and first at ETH and then hopefully at other places too. So that's the work that I do. So my talk today is, the first part is the research part on productive failure. And then I'll show you some evidence on how we've translated that, and then go into learning technologies, which is the more applied part. Okay, so that's the thing I'm going to do. All right. So this is a paper, maybe 35 years ago. Exactly, right? So this is a paper that came out in 1988, Alan Schoenfeld from University from Berkeley. And he wrote this very famous paper, When Good Teaching Leads to Bad Results. And they went into classrooms of very good teachers. If you were in that classroom as an expert, you would say, oh, this was a very engaging, well-explained lecture. If you ask students, did you learn something? They'll say, yeah, we learned a lot. We feel that we learned a lot. So by all accounts, these lectures were really good. But when the researchers started to probe student understanding of the underlying math concepts, they found it was very shallow. So how is it that very good lectures, engaging lectures, still lead to shallow understanding? And this is a problem we've known for a very long time. We talk about revolutionizing, innovating. Well, this is a really big problem to solve. Because the problem here, to define it, is not that we learn poorly from bad lectures. The problem is that we learn poorly from very good ones. And that's very hard to wrap around, because we're so used to, it's so counterintuitive. How is that possible? So why does this happen? I want to talk about just two causes. There are many causes of this problem, but just two causes from a learning sciences perspective. I'm going to do it with two thought experiments. First one is on seeing. Now imagine you're in a movie. You're watching a movie in a cinema. It's a very entertaining, very engaging movie. Imagine the person sitting next to you is an acclaimed director, somebody who's an expert at making movies. You watch the movie, you come out, and I ask you a question. Hey, did you see the same movie as the director? I said, yeah, of course, I was sitting next to the director. I saw the same movie. But if I asked you, did you see what the director saw? Chances are you would say no. Because seeing is not just a perceptual exercise, it's a cognitive one. right? And decades of research and experts and novices suggests very clearly that given the same stimulus, could be a movie, could be a diagram, could be a piece of art, could be written text, could be poetry, could be mathematical proofs, whatever. Given the same stimulus, experts see very different things from novices. We all know that. Experts tend to see deep structure. Novices remain superficial. So what implication does this very fundamental, robust finding from cognitive science have? It basically shows that the first job of teaching is actually not to teach. The first job of teaching is to prepare the novice to see. Teaching is still important. Expert knowledge is really important. Sharing that knowledge in very clear, engaging, and structured, logically structured manner is very important. But what this is telling us is that preparing the novice first to see is even more important, perhaps, because you'll get more bang for the buck from the same lecture if you did something about this finding, right? So that's seeing. So there's a failure to see in lectures, in direct instruction. Second, we don't just want people to see things, encode critical features of a concept. We want them to be able to use them flexibly, creatively, and transfer it to novel contexts. So why is transfer, or why is flexibility so problematic? So imagine now your kids, right? Your children, like on the slide, who love to play with toys. Okay? I'm going to divide you right down the middle here. Okay? This is group 1, and this is group 2. Okay? I'm going to come to group 1 and say, hey kids, here's a new toy. You've never seen it, you've never played with it. Do you want to play with it? Yeah, it's hard to tell when I go into rhetorical and yeah. All right, let's try that again. You want to play with it? Yeah. Okay. All right. Here's a new toy. Play with it and play as you like. And observe how you play with it. Then I come to group 2 and I say, hey kids, here's a new toy. You've never seen it, you've never played with it. Do you want to play with it? Okay, a little bit more enthusiastic. But wait, you have never played with this toy. So let me show you how to play with it first. And then you can play. So I show you how to play with this toy. You know, this has certain features, I show you, and then I say, now you play with it. And I observe, and I tell you, play as you like. Which group, 1 or 2, would be more inventive, more creative in playing with the toy? 1, in spite of their lack of enthusiasm. Group 1 always has the hardest. All right. And how do we teach? Group 2. All right. And so we need to start imagining concepts, ideas, as not tangible toys, but conceptual toys. And part of how we encode information in a flexible, adaptive manner is really learning how to play, tinker, and fail with these toys. Okay? And the more we can do that, the better the flexibility of encoding. Our current models of instruction, as we just agreed, is direct instruction, and the logic is very simple. The best way to teach somebody something new is to clearly tell them exactly what to do and how to do it, right? And how I try to solve this problem of seeing and flexible encoding is through a program of research that I've developed over the years. It's called Productive Failure. It started out not in such a linear fashion as I'm talking about it now, but it really started out at a bar in New York and doing my PhD studies. And we said, oh, if learning from failure is so intuitive, it's so compelling, then why do we wait for it to happen? What if we could design for it? What if we could design for it in a safe way and then bootstrap that for learning? What would that look like? And that turned into a 2-phase design where we don't start with instruction, but we start with this failure-based activation problem solving. Okay? I call it the problem solving or the generation phase. And once students have engaged in that, we go into the instruction. Like I said, instruction, expert knowledge is really important. So that has to come. But first, there is a preparation, or what Dan Schwartz from Stanford calls a preparation for future learning. Some of you might be are familiar with that concept. Okay. And like I said, it's not just any way, it's a set of design principles. There are ways of designing these safe failure-based activation activities, the problem-solving activities. There are principles for designing how students are going to participate. And really, it's about creating classroom cultures that are supportive of such interventions. Okay, so this doesn't take place in a vacuum. If you want to read more about the detailed principles of how you design, the paper's there. So I'm going to now give you a concrete example from a math classroom, well, how this plays out. So this is the lesson for 14, 15-year-olds. It's a lesson on standard deviation. Being researchers, we all know what that is. Students coming into this classroom have probably never heard of this concept. It's a very important mathematical concept. So instead of instruction on it, we say, okay, here's 3 football players or soccer players. Here are the number of goals they've scored over the years in the league. Your job is to design as many ways to decide who's the most consistent player. So if you're a 14, 15-year-old, you know some math in school, and you're given this challenge to invent as many ways, not one, but many ways, what would you do? Not a rhetorical question. Could some ideas? What might you do if you don't know the concept yet? Minimum, maximum, average. Yeah, you've learned this in school by then. Yeah, surely. Yeah. Look up the definition on Wikipedia. Yeah, consistency is a very interesting word. And there are some very nice conversations that emerge when people look it up, because a straight F student is far more consistent than a person who gets A's and B's, right? Mathematically, that's true. All right, any more ideas? Yes. Some patterns. How might you look for patterns? Eyeballing. Yeah. All right. Yeah. Yeah. Very good. Yes. So but that's an important point. So this is a curated activity where the tools have to be carefully chosen. Yeah. Any other ideas for what students might do? Visualize it, yeah, draw graphs or something, pictures and graphs. So I'm going to show you what students actually do. And this happened in about 30 to 45 minutes, given whatever constraints on timetable there are, okay? And this data comes from thousands of students. I'm going to show you the typical representations and solutions that students generate. The typical ones. Yes, you want to? Yeah, so yeah, you can, but in this phase we restrict that because it's activating the cognitive system, right? So yeah, you're right. So people do averages, totals, but we know they're going to use them, so we keep them the same. That's one of the principles of design. You need to anticipate what students will think about, and then you keep it invariant so that they reach a hurdle. It activates and then you reach a hurdle. Oops, it didn't work. What do I do next? Okay. They do tallying, they do frequency polygons to get a feel of the problem, which is good. That's what mathematicians do too. Visualization, so they draw graphs over the number of years. And just intuitively, they can talk about, oh, if it goes up and down a lot, it's more inconsistent. If it doesn't change so much, it's more consistent. Okay, so that's a good way to get a feel of the problem. Can you mathematize it? Can you quantify it? Can you be more precise? All right? Range, again, we know that they're going to use it. We make it the same. Okay, it's the evil side of productive failure. It invites you, but it makes you know that solution does not work, so that you've got to think of something else. Year-on-year deviations or differences. This is a very intuitive method that comes up almost invariably all the time. You take 1 year from the next, you take all the differences, you add them up, and the higher this value, the more inconsistent. And as people are working through that, they can see, oh, there are positive and negative fluctuations that are canceling out. So that's not fair. So let's keep all the let's ignore all the signs altogether, and let's just take the magnitude of the fluctuation. And some of them go on to average it out as well. So So that's the average magnitude fluctuation in the distribution. Hell, that is standard deviation, right? So all the components of standard deviation are already there, but they're not assembled in a way, in the formal canonical way. Yeah. And this is happening before they've learned anything. And sometimes crazy things happen. So this was a group of students who was asked to, mathematize, quantify the graph. And they said, okay, imagine if I could hold the ends of the graph. Now imagine if I could extend the graph into a rope. And what if I could calculate the length of this rope? The longer the rope, the more inconsistent. So they've gone back to Pythagoras. They've divided into right angle triangles, and they've calculated the length. Hypotenuse is a squared plus b squared equals c squared, and they've calculated the length. 83 something, 56 something, 94 something. I've been doing this for 20 years, and I've never bothered to check this computation. Because the math is not in the computation. The math is in the play of imagination, creativity. And I keep emphasizing, this is happening. If this failure-based problem-solving activities are designed well, this happens in a space of 30 to 40 minutes prior to instruction. The question is, does this work? It's a nice intuitive idea, but does it work? And that's where empirical research comes in. We compare productive failure with direct instruction very broadly. We've done experiments both in classrooms as well as in labs, so controlled experiments, quasi-experiments. And we compare direct instruction, which can be conceived of as instruction followed by problem solving, typical. And productive failure is just inverting that, but with the design principles of productive failure. Okay. Theoretically, in learning research, if you design two interventions, there are always reasons to believe that one would work better than the other, and always reasons to believe that the other one might also work. So it's a theoretical matchup. So there are reasons to believe that direct instruction would do very well. Lower cognitive load on the working memory, therefore leading to better schema acquisition, right? Lower likelihood of encoding misconceptions. If you give students the opportunities to generate their own ideas, they may generate misconceived ideas. And if these misconceived ideas leave memory traces during retrieval paths, so that could be a problem, right? So that could happen. And, generation is not easy. It can lead to frustration, lack of engagement, people give up. So you've got to be right in that Goldilocks zone. Otherwise, frustration might creep in. So those are the reasons why direct instruction could work better. In productive failure, there's better activation, more deliberate and better activation, and differentiation of knowledge, because you're not thinking of the concept in just one canonical way, but you're thinking about it in different ways, right? And what differentiation does, like the number of solutions, it allows you to compare and contrast. And when you compare and contrast, that's when you start to see what's critical and what's not. It's very hard to see what's critical in just one example. It's only when you compare it, that's when you start to see critical features, right? And that could lead to better assembly, encoding, flexible encoding and assembly. And like I said, if you have a variable activation space, it also means your memory traces, retrieval paths are variable too. So when you need to use that information or knowledge, you have multiple paths to access it. Okay, so from a cognitive science point. All right, so how does this matchup fall out in experiments? We've tracked 3 different kinds of variables, the basic knowledge. So can you remember the formula of standard deviation? Can you apply it to solve some problems? Stuff that comes out on standardized tests. We find that both methods are very well optimized to achieve high levels of basic knowledge fluency. So if that's your learning goal for your students, and you're doing direct instruction, you don't need to change anything at all. Because it does very well, 95%, so very good fluency. But like that article, The Disasters of Well-Taught Math Courses, when you start probing student understanding and transfer, that's when productive failure starts to show big effects, right? Yeah. Well, I can't change the thing, but that's just transfer. I think it was 1.2. Yeah, right? No, I think those are fair comparisons, right? Yeah. Now, and the effect size on transfer was the highest. So really, that second issue of how can we encode flexibility so that we can transfer it, that's where we're seeing the most gains. But this is just my experiments. We wanted to find out what's the universe of productive failure comparisons out there. So 2 years ago, we did a meta-analysis with my then doctoral student, Tanmay Sinha, and we asked the question, okay, we've been doing this for 15 years, 16 years. How many experimental comparisons are out there? Luckily, the work was picked up, replicated, attempted to be falsified, and so on and so forth by many people. And we found 166 experimental comparisons comparing productive failure with direct instruction. And we found the average effect size to be 0.34. And if it's done to high fidelity, because when you implement productive failure, you could implement it poorly, or you could implement it very well. So from the papers, we also coded for how they were implementing it in line with productive failure principles. And if it was done to high fidelity, then the effect sizes were almost 0.6, right? In education, what's a good effect size? That's and sometimes it's good to look at benchmarks. So if you could look at a learning gain from a good teacher for 1 year, and if you could quantify that as 1 unit, the average effect size for productive failure is twice that. Sorry, the thing is blocking again. But if it's done to high fidelity, it's 3 times that. You can't see it, but it's there. Okay, so we're not talking about incremental stuff here. Like, it's really making a big difference. Practically speaking, if you implemented productive failure, your kids would appear to be performing 1 to 2 years ahead schooling. So that's the practical significance of the work. And we have done this, and we have scaled productive failure in the Singapore math curriculum. Right? So it's not something that remains just in a lab. Yes, the control experiments are in the lab, but then we've also managed to scale it into the entire Singapore, the pre-university math curriculum or stats curriculum. Right? So I want to end the first part of my talk with just going into a bit of the mechanisms. And I'm going to talk about 4 umbrella mechanisms, but the research behind it is all the sub-mechanisms as well, but just broadly speaking. The first mechanism, I call them the 4 A's. First is activation. We've already talked about it. We make sense of new information by activating prior knowledge. What productive failure does is it deliberately activates a diverse set of knowledge components that students already have, or they can generate, okay? So, and that activation is very key, because what that does is that it builds awareness in students that there is a gap. I've tried 3, 4, 5 different ways of solving the problem. They don't seem to work fully or optimally. There is a gap. You come into a direct instruction classroom, there's also a gap. Oh yeah, I will learn something new today, which is also a gap. Students are aware they will learn something, but this is a deeper kind of a gap. They know specifically, not just in a general sense, okay? And what that does is it also builds an affect. We've studied situational interest. So students coming into productive failure, the lecture component, or the instruction component, have very high interest in wanting to find out what the method, what the canonical solution is. Okay? We've studied the emotional roller coaster that they go through. And we're finding that students get frustrated. They feel shame. They feel guilty that they can't solve the problem. But you know what? Negative emotions are not always negatively correlated with learning. We're finding some of these emotions are actually positively correlated, provided they're done in a safe way. Okay? So the emotional roller coaster is really interesting as well, because we're used to thinking, let's make everybody happy, let's make it all fun, let's make it all easy. And none of those things are correlating with learning. Okay? Now imagine a person's cognitive system is activated, they're aware of what the gap is, and their affective state wants to bridge that gap. At that point, if an expert comes and assembles it, that's what creates the powerful learning effect that we call, that's what turns failure into something that is productive, and hence productive failure. All right? So that's the learning model. Now we go into learning technologies. We want to now, as with any learning models, we've covered 2, direct instruction and productive failure. Those are 2 learning models. Now, when you build learning technologies or educational applications, I start to think of learning technologies as 3 components. First, you've got to know what your learning model is. Sometimes it's just intuitively designed into it because that's how things have been done. But sometimes it's more explicit, right? You got to think of content. What exactly are you teaching? Are you teaching, and I'll go into this. And finally, you've got to exploit the affordances. So you mentioned all the affordances of gamification, virtual reality, interactivity, visualization, simulation, AI, and so on and so forth. Those are the affordances and the user experiences that you can exploit using technology. So anytime we build an intervention or an EdTech application, and we do several of them, we need to specify these three very, very clearly. Okay, so what I'm going to do now is I'm going to go into each one of them and use it as an analytical model to say, okay, here's a learning intervention out there. Let's examine one component of that. Okay, so recently we went into what you're all familiar with, a learning model called flipped learning. Have you heard of it? All right. So we did a meta-analysis, right? We're together with John Hattie, Irina Grossman, and Tan Messina, okay? And we wanted to do this because we wanted to understand what is the effect of flipped learning as a learning model, right? And where is that effect coming from? So theoretically, flipped learning, proponents of flipped learning argue, how many of you actually do flipped learning? Okay, lots of you, right? And it's widely practiced. You know, theoretically, the argument is let's move the passive content transmission or whatever you want to call it online so that we can use classroom activity for more active learning. So a more productive use of actual classroom time. And if you think about direct instruction, it starts with instruction followed by application or problem solving. And if you think about flipped learning, you've just moved the instruction component to online, and you've kept the problem solving or active learning components to the classroom activity. Has the learning model changed from direct instruction? No, it's still the same. The underlying learning model, that's why it's important to look at the learning model, right? Not be blown away by technology, but look at the learning. The underlying learning model is the same. And if the underlying learning model is the same, why on earth do we expect it to produce better effects? That was the question we were asking. How is it possible that you keep the learning model the same and then you're somehow magically expecting innovative breakthrough effects? We answered this question empirically, okay? So when we looked at meta-analysis, there were already 46 meta-analyses on flipped learning out there. And as being academics, we found a reason to do one more. Now, it was a very good reason. It was a very good reason. Okay, we culled 173 studies based on our criteria of experimental comparisons. And what we did differently, we found that in none of these 46 meta-analyses that actually coded for what was actually happening in the online and the classroom components. What kind of activities were happening? Were there active learning activities? Were there passive learning activities? What was happening? So we coded both the in-class and the online components based on a typology. The paper's out there, right? Suffice it to say now that it was a very detailed coding into, broadly speaking, active and passive learning activities, okay? What did we find? We found that there was a positive effect of flipping. How is that possible if the underlying model is direct instruction? That doesn't make sense at all. It was actually quite strong, 0.41. A very healthy effect size. But there was a lot of heterogeneity. You're familiar with heterogeneity, right? That means there's no true effect size. It's very hard to put it's like, you know, trying to grab a fish, but it slips out, right? There's no true effect size here. So then we coded. And when we started looking at the codings, we found that instead of having more active learning in class, there was actually more passive learning. So there was passive learning online, and then a little bit more passive learning in class, which may agree with your experiences as well. So, which means that the effect of flipped learning was actually not coming from active learning, because active learning was largely absent. Right? The effect was flipped learning was actually coming from more time on task, more exposure to the same content. Okay, so the underlying model is still the same. So of course, in direct instruction, you increase time on task, you will also increase the effects. It's the basic effect in cognitive psychology, right? And that's exactly what we found. The greatest impact on the outcomes was the presence of an in-class lecture. Think about that. It literally means that the instruction model is just repeated most of the time. So this is on average, right? And because we had 173 experimental comparisons, in some direct instruction, the non-flipped courses, the direct instruction was done very well with active learning methods. So when you incorporate active learning methods into your normal instruction, the effect of flipping vanishes. Which means that it's not about flipping, it's just about active learning. Design active learning well. Okay? Otherwise, you're just perpetuating the same underlying model as direct instruction. You're increasing the time on task or exposure to content, and that's elevating. And believe it or not, this is the first meta-analysis that's actually coded and showed what is actually happening against what is theoretically supposed to be happening. Right? And this is what I call digitization without transformation. And if you look at EdTech applications, EdTech interventions, you're a community that's really familiar with. There's a broad pattern that plays out. There are some interventions that are very powerful, they're very disruptive, and they have strong science behind them, but they rarely scale. Things that do scale actually have very low effects, but they scale because they perpetuate the same culture, the same practice. So PowerPoint scaled easily because it perpetuates the same practice. Productive failure is harder to scale. Knowledge building is harder to scale. Collaborative learning may be harder to scale, so things like that. And amidst this, we didn't go looking for it. Amidst this, there was another effect where in some of the flipping interventions, did I just say flipping interventions? Some of the flipped learning interventions, they had problem solving before the in-class lectures. And we found that that had a significant effect. So just building up from the basis, we could say, well, how do we then design flipped learning using a productive failure model? And then Hati and I and my colleagues, we proposed this 4F model. So from 4 A's to 4F, still consistent, right? And we call it the fail, flip, form, and feed, okay? So the fail phase is similar to the generation phase in productive failure, okay? You create those spaces. The flip phase is, the lecture, the actual content delivery that builds on that. And then the fix and the feed phases are assembly phases, integration, assembly, and feedback phases, okay? Again, the paper is available, open access, you can have a look, right? So if you look at productive failure model as problem solving followed by instruction, the flipped learning model is really the fail, then the flip, and then the fix and feed, right? Which are more in the orangish to keep up with the color scheme, right? Then we tested this model at ETH Zurich. We took a class that is really hard, one of the hardest classes at ETH Zurich, probably at Vienna as well. It's the linear algebra course that all students have to take. We are a technical university, so everybody, and it's really abstract. Okay, and it follows this lecture tutorial system. There are 600, like much bigger than this room, and every week they come in for lectures and then they have tutorial sessions. What we did was we designed the fail component as problem-solving activities online. Okay, these were 30 to 40-minute activities for the course for the entire year, but not for every lecture, only for some key major topics. So we chose 10 topics with the lecturer, and just for those, we designed these problem-solving activities. And then they went into the flip phase, which was the lecture, then the feed and the tutorials, fix and feed in the tutorials, okay? Historically, this has a 55% passing rate. That's it. Our intervention amounted to about 8 hours for this entire year-long course. Just 8 hours, less than a day's work on the part of students for this entire year. So it's a very small dose. What would be a good or an impressive improvement in passing rate, I put you on the spot since you're vice rector.
65.
So for 10%, you will say, we're going to use this. Okay. He's on record now. Any other takers? Just a day's intervention spread out over the year for a year-long course. 75%. There is greed in this room. I like it. So yes, in the first iteration, we moved to 10%. But as I said, PF, productive failure, is about designing fidelity, so increasing fidelity with iterations. So in the first iteration, we achieved 65. In the second iteration, we achieved 75. Pandemic happened. We went down to 70. We are now back up to 75. And this will now stay the course. It's a doctoral students project that I'm just presenting here. Okay. What this shows is like, you don't have to radically change things. If you can use the science, what the science is telling us, even surgical interventions designed appropriately, well, can have massive improvements. Now, politically, that's another issue of improving passing rates by 20%, because then people have to deal with large student numbers. Okay. Now come to content. In content, I just want to make one point. It's not about domain content. It's about what kind of content you're focusing on. So here we look at theories of expertise. And if you look at deep expertise or adaptive expertise, you find that experts know a lot of knowledge. We call it explicit knowledge. These are the constructs, the grammar, the rules, the theorems, ways of thinking, right? These are the explicit, so you can talk about it, you can read about it, you can lecture about it. That's the explicit component. But there's also tacit components that you can't make it by definition, you can't make it explicit, but they can be learned in activity, in situations, in context. Even experts do not know why they make certain decisions at certain points. That's the kind of knowledge that's also very important. So good experts or adaptive experts have a very strong coupling between the explicit knowledge and tacit knowledge. Now, I've used this slide for a number of years now. That shows how hardworking I am. But the point that is now hidden, but the point I've always made is if your focus is on explicit knowledge in the content that you're designing in your interventions, explicit knowledge can be codified. And if it can be codified, it can be automated. And if it can be automated, enter ChatGPT and large language models. We've known that for a very long time. The volcano has only just erupted, but it was brewing for a very long time, right? So what we need in our interventions is a coupling, a shift towards the explicit, from the explicit to a coupling between the explicit and the tacit. How do we design that content shift is critical. If you keep designing educational applications that focus entirely on explicit knowledge, you will become obsolete sooner or later. But the moment we shift into what is more human from an activity standpoint, from an expertise standpoint, if you can create that, then that would be really powerful. And that's the only point I want to make in content. There are many others, but that's the only one. Last, affordances. You will see a lot of affordances. I've already talked about it, like interactivity, visualizations, multimodal representations, blah, blah, blah. Okay, I have a project and you have projects and covering all of these affordances. And they're very exciting, very good work. The one that I want to talk about today, because a lot of people are talking about, is personalization, right? And people are talking about in ways that are quite frankly unscientific and dangerous. Okay, I'm not against personalization, I'm for personalization, but I'm going to tell you why. Because people are talking about, wow, this is the holy grail. Let's personalize learning entirely. Can you imagine what it can do for a child if the entire learning experience is personalized to his or her needs? Can you? The child, can you imagine what that would do? Think about it. A child goes through their entire schooling, educational experience where everything is personalized to their needs. How would they enter the world? No, so if you just think through the implications, it's problematic. Personalization is good, but you need to think it through. Okay, because the question then becomes, what should we personalize to? What does the personalization vector look like? Do we personalize to learning styles, preferences? No. But there are apps that do that. Oh, I'm a kinesthetic learner, I'm an audio learner, I'm a visual learner. It's all rubbish. It's a multi-billion-dollar industry, but it's rubbish. Do we personalize to attention? I can only watch 1-minute videos, so let's give them 1-minute videos. Our cognitive capacities have not changed. Our design has changed behavior to shorten attention span. Cognitively, nothing has changed. Nothing can change in such a short time, right? So what do we? So that's a critical question when we talk about personalization. What do we personalize to? Do we personalize to your current knowledge state? Yes. Do we personalize to your current emotional state? Maybe. But do we personalize to styles and preferences and needs and whims and fancies? No. Right? So we have to be very careful how we look at personalization. Right? So what I want to start moving the personalization conversation is from personalization to adaptive. We don't need to think about personalization as much as we need to think about adaptivity. Yeah. So that learners build adaptivity, environments that adapt to the learner, but also learners have to adapt to those environments, because that's the only way you develop adaptivity. Okay. All right. So my vision, really, when productive failure meets learning technologies, is to really have cutting-edge models of learning and be very clear about those that are embodied in learning technologies. We're not talking about delivering incremental effects. We're talking about delivering breakthrough effects, not 10, 20%, 2, 3 times, more times, and that are focused on developing adaptive expertise, not just explicit content knowledge. Okay, with that, I thank you. I look forward to your comments and questions.